Okay, we got 3 days left in the semester. Can you believe that?
Yeah.
Oh, okay. All right. So we got today. What I would like to do is I would like to review solutions and acids and bases. We're gonna try and kind of cruise through this as quickly as possible. There's going to be a little bit of, you're going to need your calculators a little bit. It'd be nice if you had your magic green or blue sheet. You lost it again? Oh, okay.
Black sheet.
There's blue sheets way up here.
Yeah, it matches your golf.
Well, at least you're confirming that it's golf.
So you're confirming that you like golf.
Not curving.
That's not else.
Who's that mean, John?
On your blue sheet, I can't remember. I can't remember if we're talking about the percent or parts per million or anything like that. I don't think we are. No, we're not. Okay. So just to let you know, just as a heads up, if you look way down at the bottom of your blue sheet, it's got our solutions formulas. So the CIVI equals CFVF. Do you remember what that is? It's okay. Yeah, that's concentration and volume. So that's for dilutions, right? If you're performing a dilution. And then we've got percent by volume, percent by mass, percent mass by volume, and then parts per million. And you can do that using unit analysis, just like as a heads up, just so that you're aware. We're gonna review for about a half an hour, hopefully, or maybe 35 minutes. Then we're gonna go out in the lab, and we're just gonna do some stations activities. Hello, this is Graham. Good, how are you? No. No. Yeah. Absolutely. Thank you. Bye. There we go. Perfect. Okay. Solute versus solvent. Can somebody tell me, describe for me, what does solute or solvent mean? What was that, Idris? Good, that's awesome. Yeah. So let's draw a little picture. So if we're adding, right? If we're gonna add a scoopful of something, and the particles in there, okay. So what I want to know is what is the liquid or sometimes the gas, okay? What is the liquid or sometimes the gas that's doing the dissolving? Is that a solute or a solvent?
Solvent.
So the stuff doing the dissolving, right, is our solvent. Doing the dissolving. And what I mean by that is that it is the thing that's dissolving the solute, right? The solute is being dissolved. So that solid is the solute, and whatever the liquid or the gas that is doing the dissolving, that's the solvent. In most cases, what's our solvent? What's the thing that water. Yeah, most of the time. Does it have to be water all the time? No, it can be things like ethanol or methanol sometimes, or we can do things in organic solvents, like gasoline is mostly made out of something called like octane or decane or something. So So there's all sorts of different solvents out there, but the vast majority of the time we're using water because water isn't dangerous to anybody, and it doesn't, or it does a lot of dissolving. It dissolves lots of things, so we're really happy with it. If we want to calculate the concentration, so determine the concentration, there's a bunch of different ways we could do this, but I want to say the amount concentration of a solution of calcium hydroxide if 3.50 grams is dissolved in 0.150 liters. So first thing I want to ask you, it's just saying, give me the concentration. I'm putting this thing in water, give me the concentration. What are the units for concentration, for amount concentration? Moles per liter. So we're looking for concentration in moles per liter. Good. Do we have any of those units? Yeah. We've got liters, right? So what's the other unit that we want? Moles. And we want moles on top. Do you have moles in here? No. So what can we do? The molar mass. You want moles and you're given the mass, so let's get the molar mass. The first thing we need to do, we've just got to figure out, well, what the hell is in calcium hydroxide anyways? What is the formula for calcium hydroxide?
Ca.
I don't know. I just heard somebody say CaOH.
Yeah, that's right.
That's correct?
Yeah.
It's definitely not.
What?
It's 100% not correct.
I can't see the change.
That's not my fault, just because my fat head's in the way of the periodic table.
Yeah.
Get out your periodic table if you need it.
Or you could just cut your head off.
I don't know if you heard that, but my head is being a nuisance to John because he can't look through my head to see the periodic table. So his solution was to cut my head off.
I was saying that for
In jest, I know.
No, I was saying that for Andy.
Okay, so what's the molar mass of calcium hydroxide? Like, are we comfortable calculating the molar mass of things? Yes. Okay, so you tell me what that is. I hear a lot of sighs going on, but I don't hear a lot of calculating going on. Maya, what'd you get?
It's perfectly fine. There's nothing wrong.
74.10 grams per mole.
Like how you
That makes sense to me. Okay, so this thing has a molar mass of 74.10 grams, and I'm not going to do that, grams per 1 mole. Perfect. So do we want to put this, the way it looks right now, into our formula? No. Why?
Flip it.
Moles goes on top. So all you got to do is flip it, right? Start with what you want. What do we want? Moles on top. Perfect. 1 mole, 74.10 grams of this stuff. Okay, I want to be very clear. You don't have to put like the unit and the thing that it belongs to because we're not talking about a chemical reaction yet, right? We're not talking about a chemical. We're just saying you put this stuff in water, what's the concentration? So you don't need a chemical reaction. How am I going to get moles per liter out of this junk? So there's 2 things I got to do. Got to multiply by 3.50 grams, and I got to divide by 0.150 liters. It's totally fine if you put this thing on top and that thing below. I got no problem with that. Does anybody know the reason why I like to put them in separate fractions? Yeah, because is the 3.5 grams, is that dependent on this volume? Was it always 3.5 grams in 0.15 liters? Every time I add 3.5 grams, it's always to 0.15 liters? No. I'm trying to show you that these are 2 independent numbers. They just happen to be 3.5 grams and they happen to be 0.15 liters, right? But here, is this always going to be 74.10 grams per mole?
No.
Well, for this substance it is, right? These are related. 1 mole of this is equal to this many grams of that, right? For that particular substance it is. So that's that. I'm just trying to show you how these units are related. But it doesn't matter. You can put the one thing on top and the one thing below. It's all good. I'm going to take a stab in the dark. I'm going to say you get 0.01 moles or something.
Close enough.
What? Nope, not even
Yep,
close?
that's spot on.
Oh, 0.315? Nah, not even close. Okay, good. Good talk. 0.315 moles. Is that exactly what it is? Like rounded to 3 significant digits? Good, lovely. Perfect. Hey, how difficult was that? Yeah, that was pretty easy? Okay, we were sure having a really, really tough time with that problem when we were talking about primary standards.
What?
Do you remember what a primary standard is?
No.
It's a solution of very highly accurately known concentration. And when you titrate that solution, it gives you a high accuracy for your concentration of your titrant. So now you know the concentration of your titrant, and you can take that and you can titrate some other sample and really get a high accuracy there as well. But where does it all start? It starts with the primary standard. We had a really hard time calculating a concentration for a primary standard like a month ago. So just keep that in the back of your mind. Okay, solubility for solids, liquids, and gases. We're going to kind of ignore liquids. We're going to say, for the most part, solids and gases. How do I affect the solubility of a solid in a solution? How can I affect that?
Heat it up.
Yeah, if you want to, would you agree, if you want to get more of a solid to dissolve into your water, you just have to heat up that solution?
Yeah.
That's not always true, but in general, that is it. That 99% of the time, that is true. So if you want to increase solubility, you just have to heat up the mixture. So what we mean by that is, if you had a liquid, right, and you had a bunch of solutes down here, and it wasn't dissolving, no matter how much you stirred it up, no matter how much you mashed it up and tried to get it into smaller bits and pieces, right, it will not dissolve. There's 2 ways to get it dissolved. You could add more solvent, but you're not increasing the solubility. You're not increasing the quantity of solute dissolved per 100 milliliters. All you have to do is heat it up. Why is heating this up going to increase the solubility of a solid? No. These solids, right? Most of the time you can think of these solids as alternating positive, negative, positive, negatives, right? So if I want to get these solids to dissolve in the water, all I need to do is I need to get them to break apart from each other. How do I get these solid ions to break apart from each other?
With energy.
I give it more energy. Would you agree that if I give it more energy, these particles, these ions, will move apart from each other and break away from each other? Yeah. So remember, in every mixture where there's a solid involved, there's a dynamic equilibrium of ions being dissolved, and at the exact same time, what's happening? Ions precipitating out of the solution. Do you remember that? Kind of? A little bit? Not even? Oh well. So what's happening is these ions, they're dissolving into the water, but at the same time, the ions are precipitating onto the crystal. Now, by heating it up, I'm increasing the speed at which one of these processes happen. When I heat it up, which process am I speeding up? Am I speeding up the dissolving, or am I speeding up the precipitating?
Dissolving.
I'm heating, by heating it up, I'm increasing the speed of the dissolving. So by heating it up, I have more leaving than are coming in. So would you agree that leads to less solutes on the bottom? Yeah, I think so. Okay. So for solids, in order to increase solubility, you want to heat up the mixture. What about gases? If you want to increase solubility, what do you want to do? Do you also want to heat it up?
You.
I don't know.
Yeah.
I don't know. Let's say you got a bunch of gas particles up here. These gas particles, I don't know, we'll call them carbon dioxide, because that's what fizzy drinks are made out of, right? Pop, sodas, things like that. Okay? So you've got, what you do if you want to make a soda is you inject some carbon dioxide into the water. Now, is all of the carbon dioxide going to stay in the water all the time? No, that's why bubbles form in your water, right? In your soda. The bubbles that are being made are, there's these pockets of gas that are leaving, okay? Now why are those gas molecules leaving? How is it that these gas molecules can leave the water? Do they have too much energy or not enough energy?
Too much energy.
Too much energy. Because if they have too much energy, they're moving fast. And if they're moving so fast that they escape the liquid. Aaliyah.
Oh, so it's, actually you can finish
Okay, sure. You can ask a question later, that's fine. Okay, so what we have, again, we've got two opposite processes. Sometimes the gas molecules are leaving if they have enough energy. Sometimes these gas molecules, if they don't have enough energy in the air, sometimes they get dissolved in the water. So what do you want to do? If you want to get more gases to dissolve in the water, which process do you want to speed up? Do you want to speed up them leaving or them entering? Them entering. So what do you want to do to the particles in here? Do you want to give them more energy or less energy? Less energy. So what does that mean? Do you want to heat up the solution or do you want to cool it down?
Put it in the fridge.
So you want to keep your pop in the fridge. Does that make intuitive sense? If you put pop in the fridge, it'll stay carbonated for longer. If you leave pop out in the sun, is it going to go flatter faster? Yeah. It's going to be gross too, so you don't want to do that. Increase solubility, you want to cool it down. You want to decrease the temperature. Okay. So we're going to talk about properties of some compounds. Let's talk about some acids, for example. Give me a very stereotypical acid. Give me an acid that, like, in your mind, that's the acid you usually think about.
Acidic acid. Acidic acid.
Stomach acid.
Do you say acidic acid? Do you mean acetic acid? Okay, nitric acid?
No thanks.
Hydrochloric.
Hydrochloric?
Hydrochloric.
Stomach acid. Wait,
Oh, hydrochloric acid. Are we okay with that?
Yeah.
Is that like, you can spot this from a boo? You can spot this from a mile away though, right? Yeah, okay, perfect. What's a base? What's a base that you, oh man, I know that's a base. As soon as you see it, what? Bleach. Anything that has hydroxide in it, right? Any ionic hydroxide at all. It has to be ionic and it has to be hydroxide. So what do you?
Sodium.
Sodium hydroxide. It could have been potassium hydroxide, could have been barium hydroxide, could have been aluminum hydroxide, right? I mean, probably most people aren't going to see aluminum hydroxide and think base, but whatever, that's fine. Okay, what's an ionic compound that you like? You see it and immediately you know it's ionic, but it's not acidic and it's not basic.
Diamond.
What?
Diamond.
Oh, yeah. I kind of just assumed you would use your own.
I know, I forgot my backpack.
Yeah, that's fine. Yeah. Okay, I didn't hear a word you said. Calcium chloride? Sure. Calcium chloride, perfect. And then what's a molecular compound that in your mind it dissolves in water, but it's not acidic, it's not basic? Sugar. Are we okay with that? See, do you want glucose or do you want table sugar?
Table salt.
C12H22O11. Good. Okay. Now, my first question to you is if you could sum up whether or not a compound can conduct electricity in one word. If you could describe one word of whether or not that determines if something can conduct electricity, what would that one word be? What? I wouldn't necessarily say. I'm being so nitpicky, and I apologize because I'm being a huge jerk right now. I wouldn't say ionic. I would just say ions. Would you agree? Yeah. If your water has ions in them, it's conductive. Do you agree with that? Because all conductivity is charges moving. So if you have a positive ion moving, that's electricity. If you have a negative ion moving, that's electricity. Okay? So think, does this thing contain ions? Now when I look at acid, when I look at HCl, does that solution have ions in it? Yes. 100% it does. Because every acid, the moment you put it in water, every acid makes at least a little bit of what? Hydronium. Yes, I know. Do you remember HCl, as soon as you put it in acid, it's going to react with water and it's going to make hydronium, right? Yep, and so hydronium is H3O+. Is that an ion? Yeah, so absolutely, acids conduct electricity. Totally acids conduct electricity. Are you kidding me? What about bases? Do bases conduct electricity? What does a base always make in water? Hydroxide. Think OH minus, right? Is that an ion? Boom, conductive. Ionic compounds. I should hear a chorus of either yeses or nos here in a second. Do ionic compounds conduct electricity?
Yeah.
Thanks for playing along, Idris. Okay, molecular compounds, do they conduct electricity?
Yeah.
They're the only things do not. They do not have any ions. They don't make ions. They're neutral molecularly. Okay, blue litmus. Blue litmus. What's the only other color it could turn? Red. So is blue litmus going to turn red in contact with an acid? Yes, it's going to turn red. What about in a base? It's going to stay blue, right? So otherwise known as no change, right? What about an ionic compound?
No change.
Is an ionic compound powerful enough to change the color of the litmus? No. Because it's neutral, there's no change. So it remains blue. And neutral molecular compounds, they remain blue. What's the only thing that can turn blue litmus red? An acid. Because it's powerful enough to add a hydrogen to it. Okay, red litmus, is it going to change in acids? No. Do you remember this? Yeah, it's just been a while, that's all, right? This was 2% of your life ago. Okay, Sodium hydroxide, is that going to change red litmus?
Yes.
Yes, it is. It's going to turn it blue. Are ionic compounds, are they going to change the color of red litmus paper? No. Neutral compounds aren't acidic or basic enough to do anything to red or blue litmus. It just stays the same color it was, right? Molecular compounds are going to be red. So, let's say I had 4 solutions, and I didn't know what those 4 solutions were, but let's say something was conductive, and it turned both red and blue litmus paper blue. What solution would it be? It would be basic. Whatever your base is, right? In this case, our base is sodium hydroxide, but whatever your base is, that's got to be the basic solution, right? It doesn't really matter whatever the base is, but it's okay. Okay. Do you remember the pH scale at all? Yeah? Here's our pH scale. What's the highest and lowest values on our pH scale? Trick question. It keeps going in both directions, doesn't it? Man, I'm a real jerk today. Holy. Okay, typically what do we say is the lowest value? 0. Like 0, 1, whatever. Okay, 0. Typically what do we say is the highest value? 14. Now I'm curious. Is the 0 or the 14, which one is basic and which one's acidic?
0 is 14.
Okay, yes, good. So 0 all the way up into a certain value is acidic. I'm being very mysterious. What is that certain value? 7. Good. Hey, perfect. Okay, now what I want to know is the hydronium concentration. The hydronium concentration at a pH of 7. If we put up here what our hydronium concentration is for all of these, hydronium concentration for pH of 7 is 10 to the negative 7 moles per liter. Do you remember that?
Yes.
It's a logarithmic scale, right? For those of us who are in Math 30. So this number represents the power on the concentration. Loosely translated, it represents the power on the concentration. So what pH would a solution of 1 times 10 to the negative 3 be? It'd be a pH of 3, right? So the stronger the acid concentration, the lower the pH value we give it. Okay, the closer to 0, the more negative it becomes. There are some formulas for pH, POH, hydronium, and hydroxide that we have to remember. And we're going to go through this. Calculate the pH if the hydronium concentration is 3.65 times 10 to the negative 5. We're looking for pH. Yes?
Can you draw that chart, please?
Yes. Do you want me to draw the chart?
Yes, please. It really helps, actually.
How many people memorized the chart?
I did, but I forgot.
And then forgot it.
Oh,
Yeah. Okay. So what we do is we put hydronium in the top left, and we put hydroxide in the top right. What value, what other mathematical value is associated with hydronium? Really closely related. pH. So we've got pH, and what other value is really associated, well associated with pOH?
Interest.
Does anybody know either of these calculations? Either one of them? Negative log. Okay, we got two different. Okay, so if we want to go from hydronium to pH, the pH, because it's a power, it's based on a logarithmic system. So it's negative log of the hydronium. If we want hydronium from pH, hydronium is 10 to the negative pH. How do we connect pH and POH together? When we add them together, what does it have to equal? Good. So pH plus POH has to equal 14. And if you know anything about powers, you can actually, there's something a lot more powerful going on here. Get it? But there's something a lot more, there's something like way more important going on here that we'll talk about at the chemistry 30 level. If you know anything about logarithms, if I take the, okay. So we can go from POH to OH. Now, do we even have to write these down?
Maybe. We'll see.
It's the exact same thing, except instead of pH, it's POH. And instead of H3O, it's OH. H3H. Okay, so if I want to go from POH to hydronium, how do I go from pH to if I want to go from POH to hydroxide, yeah, it's 10 to the negative POH, and if I want to go down here, it's the negative log of the hydroxide concentration. I want to be very clear for those of us moving on to chemistry 30 next semester. And for those of us who are moving on to chemistry 30 next semester, that like these equations don't go away. You can't just erase your mind at the end of the semester, because on February 3rd in 3 weeks, we're just gonna kick right off where we started. Boom, we're gonna start off again right where we left off. Okay? So for chemistry 30, it's going to be like half a day of review, and then you're jumping into new stuff. Just for those of us who are moving on. Okay. So calculate the pH if the hydronium is 3.65 times 10 to the negative 5. How do you get pH out of anything? How do you get pH?
Negative log hydronium.
Negative log of hydronium. pH is negative log 3.65 times 10 to the negative 5 moles per liter. So let's see if I can do this in my head. That's going to be 4.37. Okay.
Yeah.
Okay, give me like 5 decimal places.
4.3770.
Okay, sorry. Start from 4 points. Say
4.4377077136.
Okay, good. What's the actual answer? Take a long, hard look at this. What's the actual answer here, Maya?
4.438.
4.438. How many significant digits? No, everybody just shut up for a second. Okay? No. It's okay. It's okay. No. It's a little harsh, but I just want you to just don't worry about it right now. Look at the concentration. How many significant figures? 3. What's the only weird rule for significant digits? Cassidy. What?
You put it after the decimal point.
Only for pHs and POHs. Are we about to write down a pH or POH? then you only care about the decimal places. So 3 digits, right? Then let's write down 3 decimal places. 4.438. Done deal.
Then if it gives you a pH, then only the other.
If it gives you a pH, right? If it gives you a pH like this, what? This is 3 significant digits, right? So now we're going back to a regular everyday number. So let's put 3 significant digits in our regular everyday number. pH and pOH is the only weird thing. Okay? So we're going to try that again, except this time we're trying to get the hydroxide concentration if the pH is 10.95. Okay. pH, is that acidic or basic? Yeah. Is pH, no. I'm not saying is this acidic or basic. Is the pH, is that a measure of the acidity or the basicity?
The acidity.
It's the acidity.
What is pH measured? It's a measure of the hydronium, right? So in your mind, you have to associate pH with a measure of the acidity of something. Now, it just so happens this is very, very, very not acidic, which means it's basic. But pH is associated with hydronium. Now, what's associated with hydroxide? pOH. You can't get hydroxide unless you have pOH. Can you get pOH?
Yes.
Very easily. Let's do that, okay? So pOH is 14 minus 10.95, so 3.05. That's the pOH. Can you go from pOH to hydroxide?
Yes.
Yeah. Hydroxide is not the negative log of the pOH. It's 10 to the negative pOH, right? pOH is a power, so it has to be put in a power. 10 to the negative power. 10 to the negative 3.05. This is going to be like 9.1 times 10 to the negative 4 or something like that.
8.9.
Damn. Okay, give me 5 digits. 8.912 50 blah 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 blah. Okay? Times 10 to the negative 4, right?
Yeah.
Moles per liter. Okay, cool. Is that the answer?
No.
No, what's the answer? 8.9 times 10 to the negative 4. Because the original value gave you 2 digits, right? So your answer needs to have 2 digits. Good. 8.9 times 10 to the negative 4. Swish. Good. Okay. As quick as we can, we're going to try and answer this. We're going to write some modified Arrhenius equations. Now, do you know what inside water makes something acidic? H. Hydronium. Okay? Let's explain. Let's try our best to explain how this compound makes something acidic, makes a solution of water acidic. Do you see hydronium in here? I don't see H3O. So what has to happen in order for this thing to make H3O in water? HNO3. What does it have to react with? It has to react with water. And what is it going to produce? It's going to produce H3O. And whatever is left over. This is called the slidey finger rule. Remember that? No. You don't remember the slidey finger rule?
That's what I do.
Let's look at HNO3. HNO3, I'm going to look at it. It's under the acid column, so we see HNO3. So this is an acid, right? When it reacts with water, it's going to make hydronium, but what's it also going to make? There. It's going to make NO3 minus, right? Plus NO3 minus. Now, approximately what percentage of HNO3 molecules will do this? If I added 10 HNO3 molecules into some water, out of those 10, do you know approximately how many would react?
9.
It's a strong acid, right? So probably, do you remember what that means? Greater than 99%. Okay with that? Hey, good. Perfect. NH3, is this a base or is this an acid?
It's a base.
How do you know it's a base?
pH of 9.
It's telling you it's a base because it's got a pH of 9. So, how can this thing make a basic solution? What is a basic solution? Something that has hydroxide in it, right? So this is going to make hydroxide. I don't understand. There's no oxygen in here. How can this make hydroxide, Aaliyah?
Well, it's dissolved in hot water.
It's
And it steals an egg, yeah.
good. This thing, bases steal protons, don't they? They steal hydrogens away from other things. So the water's going to lose a proton. It's going to turn into hydronium. Now, what's NH3 going to turn into? It's going to turn into NH4 plus, right?
Say ammonia, John? Ammonia.
I said ammonia.
Ammonium. And you can see this here as well, right? NH3 is in the base column. When it acts as a base, what does it turn into? Dunna, 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 dunna. Right? Good? Slidey finger rule? Okay. Perfect. Now, is this going to react, like, out of 10 molecules, do you know approximately how many are going to react? Like,
OH is the only strong.
yeah, OH is the only strong base. So this is a weak base, right? And weak things react, in general, we're just going to say less than 50%. Like, we don't know if it's 10%, we don't know if it's 1%, but in general, less than 50%. Less than half of them are going to react. Is that okay? Almost none of them are going to react, but that's fine. Good. Okay, polyprotic. Do you remember what polyprotic and monoprotic is?
Yeah.
It's when it does it twice.
It can react as an acid or a base, but in more than one successive reaction, right? So more than one reaction. Okay? NH3. Let's look at NH3. Can NH3 react as a base more than one time? It turns into NH4 plus, but then do you see NH4 plus as a base anywhere? No. So how many reactions was NH3 able to do? One. So is that polyprotic? No, that's monoprotic. And it was a monoprotic base, right? Okay, magnesium hydroxide. As soon as magnesium hydroxide gets put into water, what does it turn into? magnesium ions and hydroxide ions. So hydroxide, can hydroxide react in successive reactions?
Yeah.
Like it turns into water, right, when it reacts. And water can technically react, but not really. I need you to understand that this as a strong base, it's not considered to be polyprotic, okay? It reacts to make water, and water is the most neutral thing in the world, so it's not, we're not going to say that it's going to give up a proton in very many situations. So we say that this is monoprotic base. What about HCl? Can HCl react a bunch of different times? No, it's a monoprotic acid. Just toss it on my chair, maybe.
All right.
Yeah, that desk's a little bit of a cluster. Okay, thank you. Have a good weekend. H3PO4, can that thing react multiple different times? Yes, it can. Just by way of an example, let's look for H3PO4. It can react one time, and then we look for that thing, H2PO4. We find H2PO4. That thing can react again, and then HPO4 2- can also react again, right? So this is polyprotic. What about CaCO3? Take a look at this compound and ask yourself, is this compound like, is it an acid or is it a base? Is it an acid? It doesn't have any hydrogens to really give away, so not really, right? What about, can it split up?
No.
Is it ionic?
Yes.
Yeah, an ionic thing split up, right? Would you agree? Yeah? So it's going to split up into calcium and what else? Carbonate. Can you find carbonate anywhere on your acid-base table? Right there. So can carbonate act as a base 2 successive times? 1, then we look for HCO3. 2, is it polyprotic? Polyprotic base. That's tough.
So the basis you like look for its added H.
Pardon?
The basis like you don't look for H, you take it away, you look for H.
Yeah, you look for adding an H. Yeah, that's exactly right. Yeah. Okay. Determine the pH range of methyl red. If methyl red is yellow, phenolphthalein is colorless, and bromothymol blue is blue. Do you remember how to do this? It's going to take 2 minutes. Okay? That's all it's going to take.
2 minutes is like here.
It's too long.
Yeah, you got that.
I don't know if you remember, but when we did this in class, people were really mad at me, but they also refused to ask me for the alternate way of doing it. Do you remember that? Nope.
How do you write it?
You write it like.
Okay, I'm going to stop you. Does anybody want a hint? Did anybody figure out the range? Roy, do you want to give me the range? So what?
7.6 to 8.2.
Anybody else agree or disagree? Yeah? Okay. So let's do this. If you have no clue what's going on, I'm not going to teach you the other method. Okay? Like I'm just, let's just draw a line, just draw a picture. Okay, if methyl red is yellow, what range does it have to be? Just if methyl red is yellow. It has to be 6 or above, which means it can't be 6 or below, like 5.9 or below. Does that make sense? So what I'm going to do is I'm going to say, okay, here's 6.0, and it cannot be this. Anything below 6 can't be that. Is that okay? Yeah. If you don't know how to do this, just draw a picture. That's all you got to do. Okay, what's the next piece of information? Phenolphthalein is colorless, right? So what does that mean? It has to be 8.2 or less. In other words, it cannot be 8.2 or higher. Do you agree? It cannot be this. So right now, what's our range? 6 to 8.2. Is that fairly obvious for people? Yeah, it has to be in between those. Now, bromothymol blue is blue. So what's the pH range that it has to be?
7.2.
6 from 6, anywhere from 6 to 7.2. So it can't be lower than 6. Do you agree? Or sorry, no. It has to be higher than 7.6, right? So it cannot be 7.6 or lower. Right? Did we just figure out our range? Yeah, this is the only range that it can be. So it has to be between 7.6 and 8.2. Is that okay? Now, what I want you to do, there's not a ton of time left, but there's still 20 minutes left. What I would like you to do is there's going to be 10 stations out in the lab here in a second. I know some of you are moaning and groaning, and okay, all right, that's fine.
I'll bring my cat.
Did you mark the test yet?
Okay, did I mark the test yet? Nope. I didn't want to waste my time because there's still like 6 people who haven't written it. So I was waiting for them to write it today. If they don't write it today, we're reviewing the test on Monday regardless. We're going to review the test on Monday. So if they don't have it written by like Flex on Monday, then I guess they're SOL, right? Because I'm not waiting. I can't wait